Okay, so in this video, we're going to be looking at how to change points in one coordinate system to another coordinate system. So we're going to be looking at changing a point in rectangular coordinates to both cylindrical and spherical, changing a point in cylindrical coordinates to both rectangular and spherical, and then also changing a point in spherical to both cylindrical and rectangular. Now, we have these identities that we have to kind of keep track of. These first set of identities are basically the same identities you use in polar coordinates. Cylindrical basically just is polar, but with z. These are the identities that we would use in spherical coordinates between rectangular and spherical. And then we can also add on a couple of additional ones for changing from spherical to cylindrical. Rho squared is z squared plus r squared, which comes directly from recognizing x squared plus y squared is r squared. And then also, if we have r squared, actually x squared plus y squared, then we can make this actual special replacement where we have going directly to rho squared sine squared phi. Rather than doing a bunch of the algebra, I find that just having this extra identity can make switching between cylindrical and spherical a lot easier. All right, so let's start with our first point, 1, 1, 3. This is in rectangular coordinates, and we want to convert it first to cylindrical, and then we'll convert it to spherical. So since we have x, y, and z, to convert to cylindrical, we don't have to do anything with the z coordinate. We just have to worry about the x and the y. So we're going to use our x squared plus y squared formula to get our r. And therefore, r is equal to the square root of 2. And then we're also going to use our inverse tangent of 1 over 1 to get our theta. And the inverse tangent of 1 is pi over 4. And that's going to be equal to our theta. Now, one thing to kind of keep in mind that in random points that are where the coordinates are not well selected, you're not necessarily going to get a standard angle. Textbook problems certainly start out trying to get you standard angles, but then again, as the problems go on, you may not end up with a standard angle, and so you will have to double check, make sure that your points are in radians. And then, of course, we may also have to consider the coordinates, the quadrant that we're in. So in this case, we're in the first quadrant because these are both positive. So pi over 4 is the correct angle. If you find that you're not in the correct coordinate because inverse tangent will only give you first and fourth, then and you need second or third, add pi to the angle, and that will get you there. So then in cylindrical coordinates, the point 1, 1, 3 becomes r first, so that's our square root of 2, then our angle, and then nothing happens to the z coordinate. Now for spherical, of course, then we're going to use this set of identities. So the theta is going to be the same. Rho is going to have to include our z coordinate. So rho squared will be 1 squared plus 1 squared plus 3 squared, which is going to be 11. And so rho is equal to the square root of 11. And then, as I said, theta is the same, but then I'm going to need to find phi. and this is probably not going to be a nice angle. Inverse cosine of the z coordinate divided by, now in the denominator, that's basically rho squared. And this is not going to be a nice angle. So again, make sure that your calculator is in radians. And I get 1.29 approximately. So let's put this approximation 1.2945 dot dot dot. And so in spherical, 113 becomes, rho was the square root of 11. And of course, it's worth also thinking about our phi angle, what quadrant it's in. Recall that phi starts at the positive z axis, that's where it's 0, and then the xy plane is pi over 2, and then the negative z axis is pi, and you should only have angles in there, so you don't have to worry about adding or subtracting anything to the inverse cosine, because the inverse cosine is automatically going to get you angles in that space. And then, again, I'll use my approximation. We could use the exact value if we wanted, but 1.2945. As I said, we could also just use the exact formula. That would also be an acceptable representation, since it's not a standard angle. All right, so that's our rectangular to both cylindrical and spherical. So now let's think about cylindrical to rectangular and spherical. So we're going to start with 2 pi over 3 and 4. So remember what this represents is this is r, this is theta, and this is z. So let's start by going to rectangular. So 2 and pi over 3 is r. So if r is 2, then that means that r squared is equal to 4. We don't really need that information because we're going to use x equals r cosine theta, and x is then 2 times cosine of pi over 3. Which is 2 times a half. So that's 1. And then do the same thing for y, r sine theta, which is going to be equal to 2 times. Now, if cosine of pi over 3 is 1/2, then sine of pi over 3 is the square root of 3 over 2. And so this will be the square root of 3. And so therefore, in rectangular, the point 2 pi over 3 and 4 will become one square root of 3 and 4. And again, the z coordinate doesn't change because cylindrical is basically just polar plus z. Now, for the spherical case, we're going to need a relationship between r and rho, and that's where these kinds of expressions come in. So we know, for instance, that rho squared is z squared plus r squared. So z squared is z squared is 4 squared, and r is 2. And so we end up with 8 plus 4 equals 12, which is rho squared. So rho, if we simplify that a little bit, is going to be the square root of 12, which we can take a 2 out of, so this will be 2 square root of 3. And we have theta because that's given. And so we need to still find the angle phi. So inverse cosine of z, which was 4, divided by rho squared, which is 12. So we're going to get inverse cosine of 1/3, which is again also not a standard angle. But again, you know, the more that you do these, the harder it is to get exact angles to work out. So approximately 1.2309 and change. And so in spherical, the point to pi over 3, 4 becomes the point. Rho is 2 square root of 3. Pi over 3 doesn't change. And then we have our 1.23 approximately. Oops. Or as I mentioned before, we can just use the exact value for the inverse cosine. All right, and then finally, we're going to look at changing spherical to cylindrical and rectangular. And so here we have rho is equal to 8. We have theta is pi over 3, and then phi is pi over 4. So we're going to have to convert to x, y, and z. And so that's when these coordinates, these things are going to be the most useful to us. So let's consider x is equal to rho cosine theta sine phi. And so for this problem, rho is 8 and cosine of theta is pi over 3 is our theta. And then sine of pi over 4 is going to get us cosine of pi over 3 we analyzed earlier was equal to 1/2. And sine of pi over 4 is 1 over the square root of 2, or the square root of 2 over 2 if you prefer, rationalized. And in this case, the denominators are going to cancel out a little bit with the 8, and we're going to end up with 2 square root of 2. And then we repeat this calculation for y. y is rho sine theta sine phi. And so that's going to be 8. But then we're going to do sine of pi over 3, and then sine of pi over 4. So we're going to get 8 times the square root of 3 over 2 and times the square root of 2 over 2. And the denominators are going to cancel again, and we're going to get 2 square root of 6 and then to get our z coordinate, if we go back to our formulas, z is rho cosine phi. So then z is rho cosine phi. So this will be 8 times cosine of pi over 4, which will also be 8 times the square root of 2 over 2. So 4 square root of 2. And so in rectangular, our original point 8 pi over 3 pi over 4 is going to become 2 square root of 2, 2 square root of 6, and 4 square root of 2. And then finally, we have to do our to cylindrical conversion. So for cylindrical, we're going to need a relationship to get R, and we're going to need a relationship to get Z. So for Z, we've already calculated that, so that we don't have to do again. What we do still need is the R coordinate, and of course the theta will be the same in both cases. So this is where this R formula comes in, and in fact, if you take the square root of both sides, you do just get rho sine phi. So that's the last thing that we have to do, which is to calculate R is rho sine phi. And if we calculate that, we're going to get 8 times sine of pi over 4, which is 8 times square root of 2 over 2, which is going to be 4 square root of 2. And so in cylindrical, the point 8 pi over 3 pi over 4 is going to become R is 4 square root of 2, pi over 3 is the same because it's theta, and then Z is also 4 square root of 2.